L'Hopital's rule is a method to compute certain limits by differentiation. When it works, it simplifies computations greatly. L'Hopital's rule applies to situations where the limit computation leads to indeterminate forms, like 0 divided by 0, or infinity divided by the infinity. Such expressions do not have a direct numerical value, but the numerical value may be assigned through limit process. And L'Hopital's rule can be used here. L'Hopital's rule says that if f and g are differentiable, g prime of x is different from 0 for x near the limit point a, and that limit of f of x and limit of g of x as x approaches a is either 0 or both limits are either plus or minus the infinity, then a limit as x approaches a of f of x divided by g of x is limit as x approaches a of f prime of x divided by g prime of x, provided that the latter limit exists. We may use L'Hopital's rule to compute, for example, the limit as x approaches 0 of square root of 1 plus x minus 1 divided by x. Here, the function f of L'Hopital's rule is the numerator square root 1 plus x minus 1, and the function g is just x. The limit point is 0. Both of these functions f and g, the numerator and the denominator, have the limit 0 as x approaches 0. So L'Hopital's rule can be used. By L'Hopital's rule, this limit is limit as x approaches 0 of the derivative of square root 1 plus x minus 1 divided by the derivative of x. The derivative of x is just 1. Derivative of square root of 1 plus x minus 1 is 1 divided by 2 times square root of 1 plus x. The derivative of negative 1 is just 0. So we get that limit as x approaches 0 of square root of 1 plus x minus 1 divided by x is now the same as the limit as x approaches 0 of 1 divided by 2 times square root of 1 plus x. And this limit can be computed by direct substitution. We get just 1/2. L'Hopital's rule applies also to one-sided limits. To compute the limit as x approaches 0 through positive numbers of x times ln of x, we first write that in the form limit as x approaches 0 through positive numbers of ln of x divided by 1 divided by x. Now the function f in L'Hopital's rule is ln of x. It has the limit negative infinity as x approaches 0 through positive numbers. The function g of L'Hopital's rule is 1 divided by x, and it has the limit positive infinity as x approaches 0 through positive numbers. According to L'Hopital's rule, the limit of this expression is the same as the limit as x approaches 0 through positive numbers of the derivative of ln of x divided by the derivative of 1 divided by x. The derivative of ln of x is just 1 divided by x. Derivative of 1 divided by x is minus 1 divided by x squared. So we conclude that this simplifies to negative x. So limit of x ln of x as x approaches 0 through positive numbers is the same as a limit of negative of x as x approaches 0 through positive numbers. But this limit is 0. L'Hopital's rule applies to limits as x approaches the limit point a of expressions of the type f of x divided by g of x. If f and g at the limit point a both take the value 0, and if g prime at a is different from 0, then L'Hopital's rule can be justified easily. Namely, then we can write f of x divided by g of x equals f of x minus f at a divided by x minus a, and that fraction divided by g of x minus g at a divided by x minus a. This is a legal rewriting because f at a is 0 and g at a is 0. So f of x minus f at a is simply f of x. g of x minus g at a is simply g of x. And this x minus a is the term that we use to divide both the numerator and the denominator. But after this rewriting, we see that in the numerator we have the difference quotient for f at a, and in the denominator we have the difference quotient for g at a. So the limit as x approaches a is the derivative of f at a divided by the derivative of g at a. And this is L'Hopital's rule. So this is a simple justification of L'Hopital's rule in this special case. L'Hopital's rule may be used repeatedly. Here we do that to compute the limit as x approaches 0 of the expression sine of 2 times x minus 2 times sine of x, and that divided by x minus sine of x. This limit is of the form 0 divided by 0 after substitution of the limit value for x. Therefore, we apply L'Hopital's rule. We get that this limit equals the limit as x approaches 0 of 2 times cosine 2x minus 2 times cosine of x, and that divided by 1 minus cosine of x. We are still in the situation that when we substitute x equals 0, we get 0 divided by 0. So we may apply L'Hopital's rule again and differentiate numerator and denominator. We get that this limit equals limit as x approaches 0 of negative 4 times sine of 2x plus 2 times sine of x, and that divided by sine of x. If we substitute the limit value 0 here, we still get 0 divided by 0. We could compute this limit by certain rewriting and using double angle formula for sine, but we may still use L'Hopital's rule for the third time. So we observe that after using L'Hopital's rule twice, we obtained that limit as x approaches 0 of sine of 2x minus 2 times sine of x, and that divided by x minus sine of x is the same as limit as x approaches 0 of minus 4 times sine of 2x plus 2 times sine of x, and that divided by sine of x. Now, applying L'Hopital's rule again, we get that this limit equals limit as x approaches 0 of minus 8 times cosine of 2x plus 2 times cosine of x, and that divided by cosine of x. Now we may substitute x equals 0. Cosine of 0 is 1. So we get minus 8 plus 2 divided by 1. Minus 8 plus 2 is minus 6, and that divided by 1 is just minus 6. So we conclude that the limit is minus 6. L'Hopital's rule applies also when the variable approaches the infinity. To compute the limit as x approaches the infinity of ln of x divided by x, we apply L'Hopital's rule. This limit is same as limit as x approaches the infinity, derivative of ln of x divided by the derivative of x. That is limit as x approaches the infinity of 1 divided by x, and that divided by 1. But this limit is 0. So we were able to use L'Hopital's rule because as x approaches positive infinity, ln of x and x both approach positive infinity. Therefore, this limit could be computed by L'Hopital's rule, and the limit is 0. L'Hopital's rule may lead to limits that do not exist, even in situations where the limit of the original expression does exist. An example of such a situation is the limit as x approaches the infinity of x plus 2 times sine of x divided by 2x plus cosine of x. As x approaches the infinity, both numerator and denominator approach the infinity. Therefore, we are tempted to use L'Hopital's rule and say that this limit is the same as limit as x approaches the infinity of the derivative of x plus 2 times sine of x divided by the derivative of 2x plus cosine of x. The derivative of x plus 2 times sine of x is 1 plus 2 times cosine of x. Derivative of 2x plus cosine of x is 2 minus sine of x. But this expression 1 plus 2 times cosine of x divided by 2 minus sine of x does not have a limit as x approaches the infinity. Therefore, in this case, L'Hopital's rule cannot be applied. L'Hopital's rule fails. This limit can easily be computed by rewriting. Dividing both the numerator and the denominator by x, we observe that this is the same as the limit as x approaches the infinity of x divided by x plus 2 times sine of x divided by x, and that sum divided by 2 times x divided by x plus cosine of x divided by x. Here we have just divided every term by x. X divided by x is 1, 2 times x divided by x is 2, so we get limit as x approaches the infinity of 1 plus 2 times sine of x divided by x, and that sum divided by the sum 2 plus cosine of x divided by x. As x approaches the infinity, cosine of x divided by x approaches 0, and so does 2 times sine of x divided by x. We conclude that this limit is 1/2. Consider the limit as x approaches the infinity of x divided by square root of x squared plus 1. Here both numerator and denominator approach the infinity as x approaches the infinity, and we are tempted to use L'Hopital's rule. We get that this limit is the same as limit as x approaches the infinity of the derivative of x divided by the derivative of square root of x squared plus 1. Derivative of x is 1. Derivative of square root of x squared plus 1 is 2 times x divided by 2 times square root of x squared plus 1. 2 cancels out, and we get that this is limit as x approaches the infinity of square root of x squared plus 1, and that divided by x. We are still in the situation that as x approaches the infinity, both the numerator and the denominator approach the infinity. So let us use L'Hopital's rule again. We observe that this limit is the same as the limit as x approaches infinity of the derivative of square root of x squared plus 1 divided by the derivative of x. Derivative of x again is 1. Derivative of square root of x squared plus 1 is 2x divided by 2 times square root of x squared plus 1. And the 2 cancels out, and we observe that this is now the same as the limit as x approaches the infinity of x divided by square root of x squared plus 1. So we started with the limit as x approaches the infinity of x divided by square root of x squared plus 1, and we applied L'Hopital's rule twice, and we got back to the same limit. Therefore, L'Hopital's rule did not help at all, and L'Hopital's rule fails to compute this particular limit. This limit can be computed by rewriting easily, because dividing both the numerator and the denominator by x, we get that the limit as x approaches infinity of x divided by square root of x squared plus 1 is the same as the limit of the expression x divided by x, and that divided by square root of x squared plus 1 divided by x as x approaches the infinity. X divided by x is 1, and square root of x squared plus 1, and that divided by x. In that part of the expression we may move x under the square root. We get that this is the same as the limit as x approaches infinity of 1 divided by square root of x squared plus 1, and that divided by x squared. Now x squared plus 1 divided by x squared is just 1 plus 1 divided by x squared, so we get that the original limit is the limit as x approaches the infinity of 1 divided by square root of 1 plus 1 divided by x squared. Now this limit can be computed by direct substitution. We substitute x equals the infinity, 1 divided by x squared becomes 0, and we get that the limit is 1 divided by square root of 1, which is 1. So we conclude that the limit as x approaches the infinity of x divided by square root of x squared plus 1 is 1, but that this cannot be computed by L'Hopital's rule. To summarize, L'Hopital's rule applies to situations where we have to take the limit of expressions of the type f of x divided by g of x, where the functions f and g either take the value 0 at the limit point or take the value plus or minus infinity at the limit point. Then L'Hopital's rule states that The limit as x approaches a of f of x divided by g of x is the same as the limit as x approaches a of f prime of x divided by g prime of x. And here we assume that the latter limit exists. If it doesn't, then L'Hopital's rule cannot be applied. L'Hopital's rule can be applied repeatedly, so it may be that the limit as x approaches a of f prime of x divided by g prime of x is still of the type where we may apply L'Hopital's rule. And then we get that the limit of the original expression f of x divided by g of x is the same as limit as x approaches a of the second derivative of f divided by the second derivative of g, and so on. But L'Hopital's rule does not work always. But when it does, it simplifies computations of somewhat complicated limits greatly. L'Hopital's rule has been named after Marquis de L'Hopital, a French mathematician who lived from 1661 to 1704. He was the author of the first textbook on calculus, published in 1696. L'Hopital's rule was first published in that book. But the rule itself was most likely invented by Johann Bernoulli, and L'Hopital also credits Bernoulli for that in the book. Johann Bernoulli was a Swiss mathematician, little bit younger than L'Hopital. He was born in 1667, died at 1748 in Basel, and he was also a teacher of Leonhard Euler. And Euler was the greatest mathematician of his times, certainly maybe the greatest mathematician of all times.